Math 3 Spring Final Review. On this video, I'm going to work on problems from the Unit 11 portion of that final review. Okay, so I'm going to do number 1 to start off with. Okay, so logs are the what power function. So this means 6 to what power is 36. Okay, so you can think of it this way. So 6 to what power is 36? Well, that's 2. So my answer for number 1 is 2. When you see ln, that means log base e. So e to what power is 1 over e? Okay. Well, that is e to the negative 1 power would give me this, so negative 1. Okay, and that's because there's a property that says if you have a 1 in the numerator and a number down here, then I can rewrite this as a number to a negative 1 exponent. Let's see, number 4. Is it number 4 next? Number 4. This means 7 to what power is 1? That's 0. 0. Anything to the 0 power is 1. Number 5. 6 to what power is 6? Well, 6 to the 1 power is 6, so it's just 1. Okay. Number 6. This means log base e. So this is saying e to what power is 1? Well, e to the 0 power is 1. 0. Let's see, number 9. Ooh, tricky. This is saying 7 to what power is the cube root of 49? Well, I know that 7 squared is 49, so that's kind of close. But I have this, and I can't have a root, so I know that a root is a 1/3 power. So I have 7 squared to the 1/3 power. But then I need it to be a single power, not a product. So I multiply those two together, and so 2 times a third is 2/3. So 7 to the 2/3 power would give me the cube root of 49. All right, let's move on to number 11. Number 11, determine which two integers the logarithms fall between. Okay, that means I can't do what I just did here. 2 to some power is not 30, and we're going to give an approximate value. Okay, so I have to think about numbers that I do know. So I'm going to write a bunch on my scratch paper. I do know that if I have a 4 here, and then 2 squared is 4, so that would be a 2. But that's pretty far away from 30. Let's see if I can get a number closer. Okay, I remember this one, 16. 2 to the 4th power is 16, but that's still pretty far away. Okay, what about this one, 32? So that one is 2 to the 5th power. I do know that 30 is between these two. So if 30 is between 16 and 32, then if I were to evaluate it, it would be between 4 and 5. Definitely closer to the 45, but definitely closer to the 5, because 30 is closer to 32. But it would still be between there. It wouldn't be like 5.2, it would be like 4.9 or something. Okay, so I would say between 4 and 5. And they have to be consecutive integers, which means it's not going to be 4 and 6, because that would be 5. Okay? So it's between 4 and 5, some decimal number. All right, let's look at number 12. We need some practice on this. Okay, so we're going to do the same thing now, but it's 4. So this means I can't say 4 to some power is 100. Okay, it's not 25. It's not 4 times what is 10. I mean 100. But I do remember this one. 16, that's my easy one. So I know that's 4 squared. Okay, but that's way smaller than 100. I think I remember there being one with a 64. 4 to the 3rd power is 64, so that one works. Because that's still too small. So I don't know any more other than that. But I could do 4 to the 4th power. That would be, well, that's 4 to the 3rd power, and then I could multiply it by 4. So if this one is 64, I can just multiply that by 4. So 64 times 4. 4 times 4 is 16. Carry the 1. 6 times 4 is 24, plus 1 is 256. And that's way too big. But it's still the next one. It's consecutive. So 100 is between 64 and 256. So that means that this number is between 3, and 4. Okay. All right, let's look now at number 13. 13 is a graph. Okay, so let me review graphing of logarithms with you. Okay, so logarithms have a parent or a transformation equation that's y minus k equals a times log b of x minus h. Okay, now in our class, Math 3, we always have a 1 there. You'll learn how to stretch logarithms with a different a value in advanced math. They're kind of tricky. Just be ready for that. Okay, so you find your HK. For logarithms, the HK is an invisible circle, so we put an open circle to show that it's not actually visible from the graph. Logarithms have a vertical line that always goes through that. We call it an asymptote because it's like a hot lava lake. The graph can't touch it. Okay, so this is all invisible. Okay, vertical asymptotes are always an equation, x equals some kind of number. Okay, so keep that in mind. Okay, your first visible key point is always 1 to the right, as long as that a is 1, and that's because if I have b to the 0 power, okay, this would be 0 away. Okay, so if this is my powers going up and down, and this is the value I get when I raise it, so I go up 0, b to the 0 power is 1, so it would be right 1. Up 0, right 1. Okay. Then the next point is from the HK, right b. Okay, and I'm going to give this shout out to Grace Pinnell because she brought this up in class. She said, well, that's because b, whatever this is, to the 1 power, so this is my power, so I go up 1 for the power, up 1, and then b to the 1 power is b, and that's why it's up 1, right b. Okay, this is closer, so the asymptote, this part of the graph gets close to the asymptote, and then here it's getting further away. So let's see, in number 13, I'm missing the h and the k, so that means my hk is at 0, 0. You are going to have that vertical asymptote, so let's go ahead and do that part right away. The vertical asymptote is always x equals a number, and that number comes from the spot where it crosses the x-axis, so that would be 0. Okay, now I need my first key point, 3 to the 0 power, so 0, up 0, from the HK, right, 3 to the 0 power is 1. Always right 1, because there's no a is 1. Alright, then I go from my HK, my powers would be 1. 3 to the 1 power is 3, so I go up 1, right 3, from the HK. Now some of you, I caught you guys in period 3 today, you are going right 3 from this one. It's always from the HK. Okay, so this distance is only 3 from this point to here. Okay, x-intercept, that's the point where the graph crosses the x-axis. Look to see if you can see it here. Yes, it touches right there, and I know that point, I plotted it there, it's at x is 1. Okay, y-intercept, okay, that's where the graph crosses the y-axis. This is a hot lava lake, remember? Asymptotes, can't touch it. I get really close, I can feel the heat, but I can't touch it. So this one is actually none, it's not 0. I know some of you are going to want to put none, I mean 0, but it is none. Okay, because I can't touch that. Domain, how far left, comma, how far right? Will I go, it's not negative infinity, guys. I can't cross that invisible lava lake, okay? I'm going to call it like a lava river, okay? It's really wide, I can't cross it, I'm not jumping over it, so my domain is 0. I get really, really close to it, but I don't touch. Because I don't touch it, I'm putting a curvy bracket. Comma, how far to the right? Well, I can go further to the right, no problem that way. Bam. Curvy bracket, you can't touch forever. Can't touch infinity. Okay, range is how far down, how far up. Some of my students are saying all reals. Yes, put an all real symbol, that's the double R. Okay, or negative infinity, comma infinity. All right, let's look at 15. And at number 15, we have a 1. Is the 1 our H or our K? The 1 here is actually the H. It's in parentheses. The H is always the number in parentheses. So I do the opposite. That's -1. There's no K. There's no number outside the parentheses to add or subtract. So the K is 0. So my starting point is -1, 0. That vertical asymptote going through. My first key point is 1 to the right of my HK. And the second point is always from my HK, rise 1, run the B to the right. Bam. Okay. Exit, intercept. Can I see it? Yes, it's right there. 1, 2, 3. Y-intercept. Doesn't touch. Can't go to the left of that asymptote, that lava river. Okay, so none. Okay. Equation of the vertical asymptote. Oh, vertical asymptote, that's x equals. Okay, so where does it cross the x-axis? Right there at 1, since x equals 1. Domain. Okay, my lava river is right here at 1. If I don't cross it, I don't touch it. So it's curly bracket, comma, forever to the right. How far down, how far up. I'm going to write it using infinities this time. It goes down forever, up forever, so that will be curly brackets around those infinities. Okay, let's see. Let's look at number 17. 17 says rewrite the logarithm in exponential form. Okay, so we didn't really do much of those in class because it wasn't in a worksheet. But we actually did do it. I just didn't say that's what we were doing. So this means 3 to what power is m, and it's saying that answer is n. So 3 to what power? The what power is n. So 3 to what power is n? Okay. So here it's b to what power is 7. We're going to put it back in logs. Okay. Remember, it's this number to what power? Well, it's b to what power? So it's b. What power? Okay, that's the x over here. Okay, so b to what power is 7? Very good. All right, so that might be kind of tricky for some of you. Here is another way of thinking about it. Okay, so if just remember this: log base b of a equals x. So this means b to what power is a. Okay, so if I look here, and I'm going from here to here, I know that the 3 is in the b spot. So I'm going to put a 3 in this spot. An m is in the a spot, so I'm going to put my m there. My n is where the x is, so that's going to go here. But then you have to memorize this. Okay, I don't have that memorized. I always have the definition memorized. 3 to what power is m? 3 to what power is m? Okay, well, let's look at 21. I didn't assign these ones, huh? Well, I did do ones like those in the study guide for Unit 11 and elsewhere if you need to see those, okay? Might come back to them if I recognize that they show up somewhere. All right, let's look at 21. 21 says expand. And we came up, if you guys were in my group during study guide for Unit 11, we came up with some rules, okay? And I'll write them down here so you guys can see them. To expand. Okay, expand means to make bigger. There are some rules when you're making things bigger, okay? Remember, to make bigger means we want more logs. Okay, so there are rules to making more logs. The rules are that no products. Okay, no quotients. Okay, those are the first two. So I have a product, I don't have a quotient. So I need to separate the product. Okay, so to separate a product, there's a property. And it says that if I have something times something, then I can separate it to the sum of two logarithms. as long as this base is the same. And each logarithm is going to have a factor on it. So this will be n plus log base b of n. Okay. So this is my n, this is my n. So it's going to be log of x squared plus log of root y. Okay. So I don't have any more products left. I don't have any quotients, so I don't have to worry about that. The next one is no roots. So how do I get rid of a root? Okay, so roots, there is a property that says if I have something to the nth power, the nth root of something, then that means that I can turn it into a fraction exponent, where the 1 is the numerator and the denominator is that same index number. Okay, so I don't have an index on this root, so I have to think about it. I say square root, that means the index is 2. Square 2, okay, so log y to the 1/2 power, so there's no equal to there. Okay, the next rule to condensing is no exponents. Okay, so how do I get rid of those? So that property is our power rule, and the power rule says that if I have a logarithm with some number to some exponent, I can rewrite it where that power is an a coefficient of the logarithm. Okay, so here I have 2 exponents. Okay, this out of the way. I have the 2 and the 1/2, so I'm going to make both of them coefficients. But the 2 goes in front of this logarithm, and the 1/2 goes in front of this logarithm, and all the way to the front. Okay, so let's see, this up here. It's going to run out of room. Okay, so it would be 2 log x. The 2 has to be on the log of the x. My plus sign is still right after the x. Then it's 1/2 in front of the log of the y. Now, do I have any products? No. Any quotients? No. Any roots? No. Any exponents? No. Can I evaluate anything? Nope. So no. Okay, let's get 22. 22, again, we're going to expand, which means make bigger, means more logs. Okay, so do I have a product? Yes. Do I have a quotient? Yes. Now, I should reverse these two, because I can't access that product until after I deal with the quotient. And that's because the product is in the quotient. Okay? So to access it, it's like it's in jail. Okay? I can't access this until I get him out of jail. Okay? So I need to separate these two. So to separate a quotient, to remove the quotient, I use this property here. It says if you have a quotient, you can separate it into 2 logarithms by subtraction, where the numerator is on the left and the denominator is to the right of the subtraction sign. Okay. So we're going to do that here. I'm going to have log base 3 of 3xy squared, that's the numerator, minus log base 3 of 4z. Now I can access those products. So I have 1, 2, 3 factors, which means I'm going to get 3 logs from this product alone. So I'm going to end up with log base 3 of 3 plus to split up multiplication, log base 3 of x plus a log base 3 of y squared. Now I'm going to separate this one. But see how all of this is being subtracted? That means I have to subtract, even though I'm going to have 2 logarithms, I have to subtract all of that, okay? So I'm going to have log base 3 of 4 minus, nope, not minus, plus, for addition, log z, log base 3 of z, okay? But why did I think minus? I was kind of thinking ahead, or at least I can pretend, okay? I need to distribute that negative, okay? So, let's see, let me get it right again. I'm going to have log base 3 of 3 plus log base 3 of x. Ooh, I got to remove that power, so it's a coefficient of the 1 over the y, plus 2 log 3 of y, minus log 3 of 4, minus, I'm distributing the negative, log base 3 of z. I need sloppy, so it's hard to write that small. Last step. Any roots? No. Any powers, no more, but I have to evaluate. In this one I can evaluate. 3 to what power is 3? That's 1. The 1 does not disappear. It stays a 1, and I have to keep the plus sign. Okay, so this became the 1. Can't evaluate that one. Can't evaluate this one. Can't evaluate that one. Minus, and I'm running out of room. Can't evaluate that one either. Okay, so this crazy guy right here is my answer. Should have just done it on scratch paper. Shoulda, woulda, coulda. All right, let's look now at number 25. 25, we want to solve this equation, okay? To get rid of an exponential, we tend to try to rewrite in the same base. So I'd want to say e to what power is 43. But that's kind of crazy. There's another method, and that is to do the log, okay? So let me remind you of our inverse laws, okay? So there's this one here that says if I have a logarithm and this is the same, and I have an exponent here, then these cancel out and I get just the exponent as my value, okay? So I want to try to apply that here. To get rid of an e, I would need to go log base e. Well, that's good because it would get me to just an x. But the problem is I have to do that on this side too. So log base e of 43, and log base e is ln. So I would say ln 3, okay? You're not asked to use a calculator. Actually, it does say use a calculator, so let's do that. ln 3, I'm going to need a calculator. You will be allowed to use a calculator on final, so if you don't have one or don't know how to use it, you can always ask me. But we're going to have ln 3, and I got 1.09. It says thousands place, so it goes tens, hundreds, thousands. Okay, so I'm going to round to where that 8 is. 6 rounds the 8 up to a 9. So it's going to be x is about 1.099. All right, let's do another one very similar to this, number 27. 27 is a bit more tricky though. So I have a similar one, I have an e, but I have to get rid of this 3 first. So I'm going to divide both sides by 3, and I get e to the x plus 1 equals 30 divided by 3 is 10. Now it's very similar. So I'm going to go log base e to both sides. Let's do it on the next slide. So I'm running out of room. Log base e to the side and log base e to the side. Okay, so these will cancel. I'm left with just x plus 1. And log base e, that's ln. Now to get the 1 by itself, I have to subtract it on both sides, but I can't subtract it from the 10. Remember, this is kind of like in parentheses. It's like the h and k. I can't subtract the h and k. So I have to put it on the outside. And you could write it this way. X equals ln 10 minus 1. But most authors, to show that you can't subtract them, will put the negative 1 here and then show that this is positive. So it's a multiple choice final. So if you see this question, you're probably going to see this solution instead of that one. Let me show you how to put it in a calculator and why it seems to be a problem. I'm going to show you this one, and you guys should know that this is the same. So negative 1 plus ln 10. I get 1.303, okay? Now, if I type it in the other way, this way, watch what happens. ln 10 minus 1. You get a totally different number. It's because I am implying that I'm putting the negative 1 in parentheses. If I want to put the negative 1 in the back, it should be ln 10, close the parentheses, then subtract 1. And now I do it the same answer. All right, let's see. 29, 30, and 31. I think I can do that without stopping this video. Okay. 29 first. 29 we are solving. I have an exponential again, but this time I have, I don't have an e, so I'm not going to use that log base e. But I can rewrite them, and this is the method I recommend whenever possible. Can I write these as the same base? Yeah. So I could write 16 as 4 squared. So that 16 becomes 4 squared. But the x plus 2 is still out there. So now they're both 4 to some power, which is awesome. So now all I have to do is multiply those to combine them. But I have to remember to multiply this to all of that, which is distributive property. Then these bases can go away. So I'll end up with 3x plus 5 is equal to 2 times x is 2x, and 2 times 2 is 4. Now I can just solve the equation. Minus 2x on both sides. And then we get x plus 5 equals 4. Subtract 5 on both sides, and I'm going to get x equals negative 1. Okay, 30. I need to condense. And there are some rules of condensing. Okay. To condense, you need to make smaller. And that's because at most you want 1 logarithm on each side of the equal sign. Okay, so how do I have at most 1 logarithm on each side of the equal sign? So the first thing you have, you can't have any coefficients to combine logs. So no coefficients. And I'm writing really big, I should probably zoom out. Okay, so no coefficients, I don't have any. So then I don't want any sums, so no sums of logs, okay? You can combine 2 logs that are separated by addition. So if I had something like log base b of m plus log base b of n, you can bring those together as a product by multiplying this number and this number. I just have to make sure that I keep that base the same. So it would be m times n. Okay. So do I have a sum? Yep, I do. And so I can bring this sum together by multiplying the 5 with the x minus 1. But I have to distribute that 5 to both parts. So it'll be log base 2 of 5 times x is 5x, and 5 times negative 1 is negative 5. Now, I want to use an inverse law to remove the logarithm. Okay, it's not divide by log base 2, it's not going to work. What you can do, though, is use this law here, which says if the log is an exponent, okay, I don't know, how about and this base and this base are the same, then these are cancel out and get just the a. So if this is the exponent, then the base needs to be 2, which means this needs to be a base of 2 also. So on this side, I'm left with just 5x minus 5. But on this side, this is 2 to the 3rd power is 8. Now I'm going to add 5 to both sides, and I'm going to with 5x equals 13. And then I'm going to divide both sides by 5, and I get x is equal to 13. 5. Good, good, good. Let's try number 31 now. Number 31, again, we want to use those laws to condense at most 1 logarithm on each side, okay? So I said no coefficients, and we don't have any. I said no sums, and we don't have any. But there's another rule that says no differences of logs. And we do have a difference, okay? So, you can combine 2 logs that are separated by subtraction using quotient of this one over this one. So this is the numerator, this is the denominator. So as long as this base is the same. So the first one on the left is the numerator, the second one on the right goes in the denominator. Okay. So I can combine them, get rid of this difference sign. So I'm going to have x plus 2 in my numerator, 6 in my denominator. Just like before, I'm going to use that inverse law to get rid of my logs. Or I can see that if these are the same, then these must be the same. So x plus 2 over 6 equals 10. To simplify this, I can multiply both sides by 6 because this means this divided by have x plus 2 equals 10 times 6 is 60. Subtract 2 on both sides, and I get x is equal to 58. All right, that's my last question. So this was spring final review for Math 3. If you're having questions or if there's a problem that you want me to go over that's not in one of my videos, please come in and see me for some extra help.